participants, and all the students. Welcome to the Scientific Talk segment of today's event. This session is a platform to celebrate the spirit of scientific excellence and collaboration between India and Japan. We have a distinguished lineup of experts who will present groundbreaking research across various domains. Each speaker will have 10 minutes for their presentation, and we kindly request everyone to please adhere to the schedule to ensure a smooth flow of the session. I truly, we are very sorry for the delay, but we would like to start off with our first presentation. To start this session, we are honored to have Dr. Avanish Kumar Srivastav, Director at CSIR AMPRI, India, who will share insights on advanced materials and innovative processes shaping the future of technology. Please welcome Dr. Srivastav.
Good afternoon to all of you. Namaste, Tokyo in Japan. I am Avnish Srivastava from Advanced Materials and Process Research Institute. It's one of the constituents lab of CSIR. Next slide, please. So this is how in short, we call AMPRI, and it is in heart of the country. And CSIR 37 labs are distributed among 25 cities in the country in north, south, east, west. And we work on biological sciences, chemical sciences, engineering sciences, information sciences, and physical sciences. All fields we cover under these 37 labs. And under different themes, we cover it. Next slide, please. So this is the tree of the AMPRI. Left side shows the departments. I'll not go in detail, but it covers all the engineering materials, starting with composite materials, nanomaterials, waste to wealth, shape memory alloys, shape memory polymers, and all sorts of exotic waste to earth materials. Next slide, please. So the thrust areas, as I said, we have lightweight metallic materials, radiation shielding, and geopolymeric materials, nanostructured materials, hybrid composites, shape memory materials, advanced composites, and then advanced processing like 3D printing, additive manufacturing, electromagnetic forming, and then very recently we have started biomimetics and biomaterials. And our vision is to create, innovate globally competitive, economically friendly, and energy efficient technology and products for the society and the country's mission. In addition to that, we have the program like Jigyasa, where school children are attracted every year, and we have crossed in last 6 years 1.6 lakhs students. In last 6 years, these students from up to 12th standard, they come here, like here students are here. And then skill development program is for the young researchers, engineers, industry engineers who have just joined the industry's skill initiative program. And we also have the CSIR integrated skill initiative program for the PhD and MTech doctorate and master's degrees. And faculty development programs is for the young teachers who are teaching in engineering colleges, IITs, ISC, and so on. Next slide, please. So just scientific output which I want to show you, that in the last year itself, more than 15 papers we have in the impact factor more than 10. And the highest impact factor goes to Chemical Society Review, that is 46. And on an average, around 150 publications we are having every year. And in last 5 years, the average 10 papers having impact factor 23.19. So this is our fundamental research. And you know the fundamental research is the base for all the kind of research we do. Next slide, please. So more detailed way how our graph is increasing from 50 publications to 150 publications. And every year, last year we have 20 patents filed or granted. Next slide, please. So these are the snapshots uh, where these are some recent scientific contributions like graphene and 2D materials, lead-free radiation shielding tiles, piezo nano generators, ultra-thin tribological coatings, electrochemical 3D printing, biosensors, antimicrobial coatings, additive manufacturing. This is first time probably we were the first to publish paper in material science engineering on additive manufacturing of graphene composites, 3D printing pressure vessels for gas containers, then graphene aluminum ion battery, water splitting and carbon capture, 3D construction printing, additive manufacturing, and then Make in India Raman spectrometer. You know, today we are celebrating National Science Day in the honor of Sir C.V. Raman. And now India has also started manufacturing Raman spectrometer after 94 years of discovery of Raman effect in 1928. From 2022, we have started manufacturing, and that is in collaboration, AMFRI, with the industry public-private partnership. Next slide, please. These are the 4 signature technologies which I would like to give some time here. First is X-ray shielding tiles. These tiles are made using the red mud, which is the waste of alumina industry, and millions of tons of waste is there, and there is no taker. And this is substitute of lead. Lead 99, normally in India we import lead, and lead we all know is carcinogenic, and there is durability problem also of lead because of heavy density. So we have substituted with this X-ray shielding tiles. Got several awards by now, and Prism Johnson is selling in the market. Second is the bamboo composites. It's alternate of teak wood. You know, bamboo is treated as a grass in India. Government of India has declared grass in 2017, and now it is bamboo composite, which is alternate of teak wood, and it is already commercialized, and 3 industries have taken, and product is in the market. Then Parali composites, those who belong to North India, here they know Parali is agro waste, paddy straw waste, and lot of burning problem is there. They burn it. Our farmers, to empty their land, they burn it, and then it creates a pollution. We have converted Parali into the composite Parali boards, and these boards you can use for housing, paneling, and everything. Again, 3 industries have taken it, and 1 industry has already started producing in the market. Fourth, of course, Raman spectrometer is proud for the country that Sir C.V. Raman received Nobel Prize in 1930, and now India has started manufacturing it, and it is in global market and competing with international vendors. So these are the 4 signature technologies I can declare in last couple of years which AMPRI has produced. Next slide, please. Yeah, so first one is this Prism Johnson is selling this radiation shielding tiles, and first set of tiles they installed in Indian Navy Hospital in Tamil Nadu state. Next slide, please. And now we are working on gamma and neutron shielding bricks using red mud. And this right side is the equipment. This equipment is designed by us only. Right side equipment which you are showing. And most probably in another 2 years, this technology will also be in the market. This is good for making bunkers and all that. And you can reduce the wall thickness of the bunkers at least by 1/3. Next slide, please. This is the output of bamboo composite. You can have the bamboo composite houses, flooring, walls, panels. And you know, a teak tree takes about 30 to 40 years to grow. And then you have to take permission from the government to cut it. But grass is treated, this bamboo is treated as a grass, and it grows within 3 to 4 years. So that is the advantage. And there is about 96 million hectare land in India, which is where bamboo cultivation is there, but utilization is very less. So this is the technology, again signature technologies. And this flooring also, this is in CSIR headquarter in New Delhi, main conference room, this flooring is used. So again, this technology is in the market. Next slide, please. Yeah, so last but not least and very important, this agro waste, paddy straw, which in North India they call it farali, burning issue. Now we have resolved this and made composites out of that, and it's a replacement of particle boards. And this technology is again in the market, and one industry has already started manufacturing. And first installation, first use is done by the Ministry of Environment, Forest, Climate Change while they were doing their renovation of their conference room. So they have used this technology. Next slide, please. So this Raman spectrometer, two models are already in the market, CTR 300 and CTR 150. 300 and 150 reflects their focal length. And C for stands for CSIR, T Technos Company, and R Raman. So that is how this model name has been given. And 10 systems are already installed, including Physical Research Lab, Ahmedabad, NCL Pune, ICER Pune, Manet Bhopal, IICB Calcutta, and so on. Next slide, please. Now, very recently, we have got electron beam, this 3D printing, and laser beam 3D printing. We are like a hub in India for 3D manufacturing, additive manufacturing for 3D models, like for polymers, for agro waste, and for civil structure, electrochemical 3D printer we have developed. So we are like becoming hub in the country for additive manufacturing. Next slide, please. Yeah, some of the components you can see here that how using 3D printing we have developed. And these are aluminum graphene composites or SS graphene composites. And these are the first applications globally. We did it on these kind of materials to change their mechanical properties and thermal conductivity. Next slide, please. Yeah, so this is another some models I was seeing outside. And this is basically the piezoelectric material that you press from one side and then it generates electricity in the other direction. Next slide, please. So we have used borophene here. Borophene is a new material and 2D material where it's a non-centrosymmetric. So when you press it, so because of non-centrosymmetric, it generates dipole in other direction and electricity generated. So that concept we have used it, and it is still in concept wise, and we have published in Nano Energy. And very soon we will transfer this technology to some industry for commercial purpose. Next slide, please. So these are some of the technologies. I may not be able to go one by one because of the time limitation. But in next slide, please. Next slide. In last about 6 to 7 years, we have transferred around 27 technologies to the market. Out of these 27 technologies, around 7 technologies are really in the market. You can see the Indian stores, shops, and all. And they are not only just low-end technologies, high-end technologies like radiation shielding, tiles, and spectrometer. And this is Raman spectrometer is the first high-end analytical instrument which India has started manufacturing so far. That too from our own Nobel laureate concept. Next slide, please. So this graph shows how the project numbers increases, like from 43, from 50 now we are having 94 projects with almost same number of manpower. Next slide, please. So this shows that how the projects are distributed from the government agencies and the industries, because it's almost 50-50% grant we are getting from government and industries, government departments and industries. Next slide, please. And by doing this, we are contributing to 7 Sustainable Development Goals of United Nations, which India has also adopted, like no poverty, zero hunger, quality education, good health, gender bias, and so on. So we are satisfying to 7 Sustainable Development Goals of United Nations. Next slide, please. So this, like I have made a chart, like in next 15 years, what institute can do in terms of advanced processes like electromagnetic joining and forming, additive manufacturing, electrochemical, 3D printing, atomically thin coatings, advanced processes, and the advanced futuristic materials like graphene, flexible nanogenerators, metal 3D printer, Maxine, Borophene, metallic foam, gold foam, piezo nanomaterials, and so on. Next slide, please. Yeah, so this is the comprehensive action plan. I'll not go one by one, but I think this comprehensive action plan works for all the labs. Like you have to find out your strength, then identification of stakeholders, skill development programs, engagement of industries, and technology transfer and licensing. Next slide, please. So this slide is very busy, but last slide. But it shows that how must we try to do the SWOT analysis, strength, weakness, opportunities, and threats. So best part is to look at the opportunities, what we have to transfer more technologies, publish papers in good journals like Nature, Science, and all, innovative research, and then collaboration with different organizations, and then interface with organizations like industries, government funded sectors, strategic sector, academic institutes, NGOs, to fulfill the government of India programs like Skill India, Digital India, Startup India, Make in India, to make the country self-reliant in terms of economy, demography, infrastructure, system, demand, and system and demand. So through our technological interventions and innovative technologies. Thank you very much for giving me time. Thank you.
Thank you, Dr. Srivastava, for your valuable insight. Thank you, sir.
I can take question or
No, sir.
afterwards?
We have question and answer session
Okay,
later.
thank you very
Thank you,
much.
sir.
Thank you very much.
Thank you.
Namaskar.
Our, thank you. Our next distinguished speaker is Dr. Makoto Ikeda, professor at the University of Tokyo's Graduate School of Engineering. Dr. Ikeda, the stage is yours.
Is it working? Okay. So it is my great honor to be here to present our recent research activities. But this is wrong. Sorry.
Sorry, sir, about the slide.
Same Makoto, but actually in design area we have at least 3 Makotos, and also the former president of University of Tokyo is first name Makoto. So it may misunderstanding you that the Makoto is too common name in Japan, but it's not so true. Anyway, okay, thank you very much. So I'd like to introduce our research activity, but it is relatively sort of the platform, the establishment. So of course to realize the advanced research platform is very important. Oh, sorry. This. So basically, let's skip for the sake of time. So basically, we have I'm now in DIDA, which is named System Design Lab in Engineering School of the University of Tokyo. But the DIDA have been just established 2019, and before that, we are with VDEC. VDEC is the VLSI Design and Education Center, which have been established in 1996 as an inter-university facility in the University of Tokyo, fully supported by Ministry of Education. And the functionality is to provide a chip design platform to entire Japanese universities, which is to provide EDA tool to design and also chip design gateway to Japanese universities, because at that time TSMC haven't yet the widespreading, so there have been less chance for academia to tape out the chip. And of course, the education is most important thing, because only tools, only design kit will not make sense to anybody to chip design. And then in 2018, we have started the name AI Chip Design Center along with the ICE, the National Institute, supported by Ministry of Economy, which have the similar functionality as VDEC, but supporting the smaller startup and industries, because the VDEC can support only academia. But the chip design in smaller in industry have also the problem. And then in 2022, we started the AgileX project, which is supported by Ministry of Education under the project XNIX. X is anything like electronics, fintronics, and anything. And we propose X as a design. And fortunately, we got accepted. And the main mission is to increase the number of designers to make the design and the chip fabrication in agile manner. Of course, and also from the last year, we have started university-wide education program in semiconductor, so that to encourage many people to learn about semiconductor inside the University of Tokyo. Okay, and then so, and in addition to that, related to the researches collaborating with India and Japan, we have conducted the research project named SciCorp, supported by the JST funding agency under the Ministry of Education. And fortunately, the University of Tokyo and IIT Bombay having the collaboration and like this. So this is started in year 2016, and we have now in the phase 2, and phase 2 will be concluded by the end of March next year. And the important thing here is that it's not only to conduct the project, but also we will initiate sort of the joint research hub in both sides, in India side and in Japan side, to accelerate future researches. So we are now planning how we can establish such kind of the long-lasting the collaboration platform. So we are working towards that. And then for AI chip design center activities, of course, this is to provide a chip design environment. But at the same time, for the academia, chip design is just designing some small test chip. But for industry, chip design means something like a designing product. To make a product, you have to have the bunch of peripheries along with your ideas. So to demonstrate that, instead of just designing one idea with one peripheries, we integrated several designs into one chip. So sort of something like a multi-project SoCs. And we successfully demonstrated the everything worked very well in very short time period. And to realize that we have this kind of hardware emulator to evaluate the entire chip up to the software level. So that is very important. And using these, the design, the process, we documented everything so that everyone can follow the similar design. That should be very good educational material at the same time. And then for the AgileX, as I mentioned, we want to increase the number of designers to the factor of 10. How we can realize that? Because the software, you can compare and obtain the result in short time period. in hardware, we need to design for maybe for the case of the big chip takes 1 hour, 1 year, and takes few months to fabricate. And software people cannot wait until that long time. So instead, we can extensively utilize sort of the hardware, the higher level synthesis tool with IP reusing. And for the fabrication, instead of sending entire chip to TSMC, we use sort of the structured ASIC so that we can manufacture only top 1 or 2 metal layers to program the chip. And I hope this works. So this is the part we introduced named minimal fab. So this is very small form factor of the machines, but everything is done inside. And the important thing is this is not inside the clean room. This is just an office space. And you can see all the processing in real time like this. It's not that they speed up the videos. So for 1 or 2 metal layers, it can process only 30 minutes. So you can just wait 30 minutes to fabricate your chip ideas. So this is part we are doing, and we already realized this kind of test chip by our students, so that we will open this the functionality to outside maybe by the end of this year, so that everyone, if you have any kind of the ideas, come to here and design your chip in say a few hours and fabricate your chip to realize your ideas. So that is what we are doing, and maybe it should be already 10 minutes. They're going to their own research. I have been working for hardware security for a while, which is very important of the source of the information. But the realizing crypto algorithm into the hardware should take quite a long time. So that's what we have been doing, and especially we have been focusing on the post-quantum cryptography, because nowadays the quantum computer is getting the advancing, and sooner or later the current crypto algorithm might be broken. So to protect from such kind of things, the post-quantum encryption algorithm have been intensively studied by U.S. The governmental institute NIST. And now last year, the FIPS have filed 3 as a standard. Of course, some more will come. So we are now intensively working to accelerate this kind of algorithm in hardware, so that everyone can utilize this algorithm for your safety. So this is the end of my talk. Thank you very much for your kind attention.
Your informative presentation, and also ending your presentation exactly in 9 minutes. Thank you so much. Next, we have the pleasure of hearing from Dr. Makoto Taiji, Director of the Advanced General Intelligence for Science Program at Riken Tree Headquarters. Dr. Taiji, we invite you to share your invites.
Okay, thank you very much for this invitation. It's very honor to me to give a talk in this symposium. So my name is Makoto Taishi. I'm a director of this Riken so-called AGES project. This is AI for Science project in Riken. But in my PhD, I was using some spectroscopy work, so I was very using some of the Raman spectroscopy. So it's very honored to give a talk here. So maybe many of you know last year's Nobel Prize for Chemistry and Physics was given to this AI. So this for the chemistry prize, David Baker and Demis Passavich and John Damper was awarded to developing some AIs to predict protein 3D structures. And physics prize got to J.J. Hopfield and Jeffrey Hinton, who developed who created the foundations of current AIs. So already this AI's position importance in science is already started. So now AI is bringing so-called this fourth industrial revolution. In this phase, this kind of intelligent tasks may be automated by AIs. So the scientific research is one of the core of our intelligent activities. So it is very important to utilize AIs for scientific research. So we established this project, AI for Science project in RIKEN. There, of course, maybe many of you already use this ChatGPT or this large language models. But of course, this large language models is also very important for scientific research. But there's some so-called domain foundation models, like this AlphaFold for protein 3D structure projections. This kind of domain models is also very important. So we have more focus on to develop domain foundation models. So now RIKEN has so-called TRIP systems. So TRIP is to combine many of RIKEN activities together in this one of this research as one research systems. So we established this so-called this AGIS project inside of this TRIP system. So we produce data by experiment and make AI models. And for this, we need some computational infrastructures, large-scale computational infrastructures. So this is project is established in last April, so it's very quite new projects. But at this moment, we have no result yet. But it will continue about 7 years more to establish whole science in RIKEN and also in Japan. So our strategy is, of course, to first we need to catch up scaling of AIs. So recently, AI models is getting larger and larger. For the example, this some of the models have trillion parameters. So we need to enlarge data size and model size. And of course, for this computing size should be scaled up. And based on these data, we like to create some multimodal foundation models. Multimodal means, for example, for the biologists, we need some genome data and some transcription data and other data. So it's very important to combine these several data into one models. So this kind of model we are going to develop. And the third point is to develop some automated research system, including the laboratory automation. Then our goal is to establish these systems and to produce some new scientific results based on these AIs. So this is current project structures. We have two domains. One is life and medical science. Other is material science. And life and medical science, we have several models we are going to develop, including some molecular scale or cellular levels and spatial models and so on. And for the material science, and we focus on the solid state, especially for the magnetic properties, and polymer science, and also some material processing, which was also given by the previous talks. Also in this material processing, we extensively use some Raman microscopy. And also we have some activities in the computational infrastructure to develop, to introduce large-scale GPU clusters. And as a common infrastructure, we establish some automated research system and large language model for science. And for this, we gather various RIKEN activities, and not only in RIKEN, but also some other universities and some research institute activities. And one of the examples is in the life science field. In the life science, we need to combine some various modalities of data from genome to this some animal behaviors. So we collect quite a lot of modalities data and try to combine them as into one foundation models in future. The one with the example is cellular scale models led by Dr. Yoshi Nikaido, who is also the professor of University of Science University of Tokyo. And here they want to create some foundation model of cellular response. Then they try to measure systematically of the transcriptome and some ribosome profiling and also some cellular dynamics images. So by combining these data, we try to create some foundation models that enables some cellular behaviors in dynamics. And then we try to develop some automated research systems combining AIs and robotic or simulation. Then we create some assumptions. Sorry, something wrong. Yeah. So AI-generated experiment conditions. Then we do some automated experiment by using robot or automated simulation by using supercomputers. Then we obtain some massive data and we retrain some AI for this next step study. So we like to create this kind of automated research system in the future. For this, we use this is developed by Ayasca manufacturing and also you can know ICE. And this is so-called Mahoro robot with dual arm. So this robot will automatically doing experiments. And in addition to this dual arm robot, we are developing some single arm robot. This is we are Niken is developing. Koji Takahashi is developing this robot, and this single arm robot is much cheaper than this dual arm robot. So we use both of these robots to automate all research systems. So then in the last two slides, I'd like to explain completely different topic. Currently, we are trying to establish some collaboration with India. So I have already also another affiliation as Deputy Director of RIKEN Center for Biosystem Dynamic Research. So last year, we have a meeting with NCBS in Bangalore. And there about 9 PIs and joined for this meeting, and I also visited. Now, currently, Professor Hiroshi Hamada, who was alumni of RIKEN, is working as a professor of NCBS and Ashoka universities. So he invited us to discuss with NCBS people, and here it's Professor Vijay Raghavan of his former director of NCBS and he's the principal scientific advisor of Indian government. And then during the meeting, we discussed about future collaboration. And of course, we discussed about many bottom-up collaborations, but we agreed to try to establish some top-down style, project style collaboration by placing joint laboratory for Indian side and also this Japanese side, and exchange PIs and also some students in future. Then next week, several young researchers from Japanese researchers will visit this Bangalore, who are this candidate for this laboratory head of the joint laboratory. And next April, we have some large symposium in Kobe, and many people from NCBS will come to NCBS and INSTEM will come to Kobe, and we'll continue the discussions. So we hope we ask for this support from the Indian government and Japanese government for future collaboration between RIKEN and India, NCBS and Indian institutes. Yeah, that's all for my talk. Thank you very much for your attention.
Thank you, Dr. Thaiji, for your insightful presentation. We are honored to welcome Dr. Renu Wadhwa, Principal Scientist at AIST, who will introduce us to the pioneering work of AIST India Dye Lab. Dr. Wadhwa, please proceed.
Good evening, everyone, and happy Science Day. Thank you for being here, and my thanks to the organizers for having me here. It's my pleasure to talk to you today. And as you see on the screen, my name is Renu Wadhwa. I hail from city of Golden Temple in the north of India, Amritsar. And I've been in Japan for last 35 years. And my training, besides in Japan, also belongs to UK, Australia, and of course, India. So today, I'm going to walk through the journey of Dye Lab, how it was born and how it has progressed to the formal name AIST India Dye Lab. We are very proud at AIST having India in the name of Dye Lab, AIST India Dye Lab. So birth of Dye Lab is marked at October 3rd, 2013, when the contract between DBT, Department of Biotechnology, Government of India, Vijay Raghavan, Professor Vijay Raghavan was the secretary of DBT that time, and it was signed by President of AIST in the presence of Ambassador of India to Japan. So although the birth is 2013, seed for Dye Lab was sown as a comprehensive MOU between DBT, Department of Biotechnology, Government of India, and AIST back in 2006. And just like 10 people had joined the signing of MOU. And then we were approached to ask to activate this MOU. And this is our journey. I'm going to describe you in one slide here. From 2006 to 2000, approximately 10 and 11, we had only the alternate symposia either in India or in AIST Japan. And this continued every year. And 2010, I proposed to Secretary of DBT to have actually a lab together, the origin of bilateral lab. And we are the one marking the history of first international laboratory in Japan in 2013. We were interrupted by the big earthquake in 2011, but the discussions continued, and finally the lab was signed from 2013. The mandatory component of this signing contract was the training component, as we also today talk about training of India, youth for advanced science, technology, and education. So we developed all these training programs I'm going to walk you through. We have workshops in bioimaging and analytic biology, either in AIST or in Mumbai, cooperated with Shimazu Analytic Company. We have CAFE. CAFE means classroom for advanced and frontier education. We have CAFE every month, and we connect to 5 Indian sites. Besides that, many other countries also joined the seminar, and this has been happening, and we are reaching series 100 this month. We have CAFE Plus, where we train. Plus means presentation learning for young scholars, where we aim to train the young students and scholars for good presentations. We train them for making good presentations, presenting on the stage, and we do that on the competition base. So we have rounds of CAFE Plus. We select the best speaker, then have them compete for the second, third, and fourth rounds, and have the grand winner and prize them and award them. This has been happening from 2015, and we change into the mentor mode from 2022. And I'm happy to see some of the mentors in my group are also sitting here Dr. Hemant is here, who participates as mentor in the Cafe Plus program. So we train the Indian kids for making good presentations, have them compete like you have the reality programs on the TV, like Saregama and the Dance India Dance, and we have the winners picked up from them. Then we have the picnics. Picnic here means the platform for innovating knowledge to international know-how. We've been having picnics as a casual symposia, either in India or in Japan, and we have completed 63 series of picnics so far. So radio is the relay of research results by audio, where I speak about the outcomes of a research paper and make a 2 to 3 minutes audio and send it by email to about 500 people. So this has been our training programs. Besides that, we have the sister labs in India who specialize in different themes in biomedicine, and these are all of our publications, and to date we have 220 publications from India and Japan sister labs under this name. So this is all about milestones of DILAB so far. Let me walk you through to the photo gallery to show you these in a bit later, bold words. And these are our sister labs. You see that all specialize in different themes of biomedicine or molecular biology. Then we have these programs I already introduced. STAR program is the one where we invite students from India. So STAR means the student training for advanced research. The student stays with us as a technical trainee from 3 months to 9 months or even a year and perform in the laboratory with us. Then we have doctor program, develop application and clinical trial oriented research. I already introduced our workshops, either the imaging or the analytic workshops. Then I introduced CAFE. This is the typical picture. For CAFE, we are 8 sites are joining. And as I said, we have completed 99 cafes so far. Then we have this Cafe Plus, started in 2015, shifted to the mentor mode. And we start with something like 40 to 50 students, take them through the rounds of competition, and finally end up with 3. We just finished Cafe 2024, and the 3 winners were awarded, first, second, third prizes and the cash money as well. This is the picture for the picnic, where we go as a symposium, group of researchers from AIST or elsewhere in Japan, combined with the people from India, and have this picnic as a very high-class platform for exchanging knowledge and changing to the know-hows. So 99 cafes and 63 picnics have been completed. This is our website, and all this information is available. You're most welcome to take a look there. And we feel very lucky and proud to be flashed on the Science and Technology policy statement when the MOUs were signed and upgraded from DILAB to DICenter programs in AIST. So, most recently, 2022, we have signed MOU with All India Institute of Ayurveda for advanced research and the projects and the training component. We have also signed MOU with ACSIR, which is the highest or the largest academic body offering PhD to the students. So we connect to something like 86 institutes in India, and with a large number of students, over 6,500 students there. And what we hope to do is that AIST, with its mandate from taking the basic research to the industry, we hope as AIST India DILAB, we also bridge between academia and industries, bringing Japanese industries to the interest of Indian marketing and vice versa. So this is all about DILAB introduction. I would also like to give you a flavor of my research. And here it is, the 35 years of research on the molecular mechanisms of stress, aging, and cancer, and hope to intervene this knowledge into the products. So stress is 100%, right? Am I right? Everybody has stress, and it's not considered as a disease. But the most critical, most serious is when stress affects you in a way that your normal cells in your body forget to stop to divide. So they keep dividing, and that is called cancer. So connection of stress or aging to cancer is most critical. And here comes the innovation, and the basis of that, the basic research is to understand why the normal cells divide only for a limited number of times, and why and how the cancer cells keep on going forever. So this has been the main theme of my research and my team's research. In this path, we have discovered two proteins originally. One is named as Morlin and the other is called CAF. So we've been building knowledge on the role of these proteins in the process of cancer. Not only that, the idea is to how to intervene their role so that we can have cancer therapy components. So in spite of going to the drug development line, we chose to do, the slides are not moving, we chose to do on the nutraceutical aspects, and in my lab, the various nutraceutical components, and with focus on the Ayurvedic herbs, has been to study their anti-cancer activity. And I show you the example by only one, ashwagandha, which is a queen of Ayurveda. This is the medicinal herb. We made extracts from ashwagandha by different ways and look at their anti-cancer activity by different models in the cell culture system and the animal models. And what we originally discovered was there is something in the ashwagandha extract that can kill cancer cells only and spare the normal cells. So we took this observation to a variety of the molecular, experimental models where we discovered the original components which have anti-cancer activity, and we also discovered the mechanism that has been largely published. And what the core finding here is, you may make a water extract, you may make an alcohol extract. Both of these have anti-cancer activity. The mechanisms by which they work is different. So this gives you the message that Ayurveda taught us several thousand years ago, that don't use individual components, but use the crude extracts or the plants. So in a way, you do not tear apart the activity components to use them together. But here we are telling you the molecular mechanisms, how they operate, so that hopefully we can take it to the botanical drug pathway, which can be more simple and safer and less expensive too. So on the normal cells front, we also discovered that the anti-cancer activity is there, but the normal cells also face the anti-stress activity. You can appreciate here the oxidatively stressed cells are dying, and with the component from ashwagandha extracts, they are happily dividing here. Same is with the UV extract, and here you are looking at the number of aging or stressed cells, which decreases if you feed them with the ashwagandha. This is like premature aging model. You see with this MAA compound, you can induce premature aging of the cells, less number of cells, more number of blue cells indicating they are aging, and that can be reasonably discovered with ashwagandha. And we've been looking into the molecular mechanisms of these anti-cancer and anti-stress activities, largely published these work already. So I wouldn't go into the detail, but say thank you to you for patient listening. And you see here AST president in the middle, and also the vice presidents there, indicating that we do have great support from them. Thank you. Thank you very much.
Thank you, Dr. Wadhwa, for showcasing your significant collaborative effort. Thank you, ma'am. Our next speaker, Dr. Tsutomu Tsuboi, chairperson of the Mobility and Behavior Innovation Forum, will discuss challenges and breakthroughs in mobility and behavior innovation in India and Japan. Over to you, sir.
It's on. Okay, thank you very much. First of all, the young students, I apologize. I only contacted almost only 1/3 of their demonstration, so very interesting your demonstration. Thank you. Today, my topics is kind of like the challenge for mobility and behavior, the innovation. That means maybe I can explain in this my presentations. You can see I made a bit. First of all, who we are. We are pretty much young organization. And so we are focused on just almost 1 year. And then we are more focused on mobility and behavior. So that's why we call it Mobi Forum. That is we are chosen for this name. And then, so our mission is to optimize for mobilities. So I have several times to visit India, but I pretty much worry about for like so much traffic congestion day by day. So maybe I couldn't visit for any visit in the other major city, but right now we are focused on the Bangalore at this time. Maybe you can see later my research. Okay. So we are now just starting how to contribute to the how reduce the traffic jam. But this is I just talking about today for the India traffic. However, even here in Japan, we have still a lot of congestions. So that's congestion means is a lot of the some impact, negative impact, such as the air pollution, CO2, the observation, and also like some kind of healthy problems. Many negative problems occurred. So we try to how to make up for a much more sufficient from these areas. Then activities is first, of course, for the mobilities. At this moment, we are more collaborate with the automotive company. So this is very important to the mobility itself. And also, we also very closely contact the municipal corporation because the vehicle itself cannot be controlled by themselves. Maybe for infrastructures, so municipal corporation is very work hard to improve the kind of infrastructure informations. However, still is some mismatch. So therefore, we are focused on the our try to now the current research activities and why this traffic congestion occurred. It's very simple. One is of course overloaded, many vehicles on the road. Because of course in India it's a pretty much good advance for the economical situation. That's good. But on the other hand side, it's so much population, so much transportation, that makes some kind of negative impact. And then insufficient traffic information. That's very important. So we also checked for the taxi drivers in Bangalore, 300 drivers, and we are asking them, are you familiar with this? Yes, because I live here. But problem is some information is not untrusted. In other words, because so many roads is under construction, sometimes they shut down and we don't know how to do it. So this is very frustrated about for like traffic informations. And also, this is pretty much normal. It's a poor road construction because of course, India has huge countries and you have a lot of the investment to improve. So it's also getting better. However, still have some kind of lack of the instruction. So first is the mixed traffic. This is not in Japan right now. And India is so many variety kinds of the mixed traffic. Of course, in like a rickshaw, and also sometimes like 4 wheels, and also 2 wheels, and also like a public transportation ongoing. And also frequently unregulated stops because this is under construction somewhere everywhere. So that is suddenly this is not you can't go through. So this is pretty much congested. The main reason why this is congestion occurred. But you can see the 2 through the 5 needs more budget, of course, improvement, and also more time. So that's our decided. We only have a new organization, only 1 year organizations. So that's why we are focused on overloaded. This number one. This is much easier for us. Of course, the infrastructure company and many people is working for through the 2 and the 5, but our organization is more focused on number 1. Then, if we can some kind of appropriate to kind of like a management, maybe let's find the solutions. Economic mobility. That's our the looking for right now. This is our the some kind of research at this moment. Here's my colleagues, Mr. Oshima plays here. He took pictures in Bangalore in the last year. And also the other one is also 2023, still like this. In Japan, not like this, but of course, so many traffic congestions that today we also I need more visit for like Delhi and also the Bangalore and Mumbai also. I heard it's very congested. So maybe this is one of the example of like the Bangalore at this time. Then it's a kind of like a lack of and so detour is pretty much difficult to find out. And also the family with the habit, because I also asking to the taxi drivers, why you don't change your route? Because I don't know, and I pretty much trusted this area. So that's why they never change the road. And also, because unnecessary is some kind of the road conditions, is some kind of the difficult to find out. Suddenly is some kind of under the road work is started. So this is pretty much unknown areas. So that's why conclusion is definitely we need some kind of trusted information. Otherwise, the never chance to go to the detour, never chance to go change for their behaviors. So these are some snapshot. What we are doing is you can see in the front is some kind of mobile phone here applications. That is we collaborate. Is an Indian the startup company. They make this kind of the smartphone solutions, and then they detected any kinds of the driving behaviors, such kind of sudden brake, hard cornering, and also hard accelerations. So though these information is coming in a minute, so we can use it. And then this kind of information is good to understand how the driver is working. So therefore, we are not focused on some navigations. We are focused on how to drive behaviors for each drivers. Then we collected all the data and then find out some kind of solutions. It's maybe some area is pretty much dangerous area, or that means the hard braking, sudden brakings, and hard cornering. That is kind of like a stress. So today I learned from the two Makoto-san presentation AI chip. It's good. And also like stress. This is also another keyword today. So we are focused on driver stress. Which area is more stress for the drivers? And then we are making some kind of maybe calculation here. It's a kind of a mathematic or science information at the moment. So young student here, are you interested or you are pretty much good at mathematics? Please join with us. So maybe let's make some kind of good modeling system. Then that is going to eventually go to AI chip. That is my dream at the moment. So here's one of the example. And then I can calculate it some kind of the stress zone, which is some sudden brake and hard cornering and accelerations. And then normally in the drivers, it's very familiar with such kind of current navigation system. We are not against for this kind of things. We are making some kind of the suggestions and the notification, which area is most dangerous or which area most stressful for you. So that kind of like a supporting system, we are working on it. So this is kind of slightly different approach. Is that we are not making for any some infrastructure improvement. No. We try to find out the current situations and there's some kind of the difficulty area to find out to mathematical calculations. So it's kind of the maybe let's say Jugato innovation. That's what we're looking for. So here's some of the process. So first, we already have drivers questionnaires and try to use for the mobile phone applications. And then our mobile forum is working for the analysis. And then try to pass over to municipality. And they also have many tons of data. which is going to allows us, oh, this is very trustworthy data. This is just a kind of like Bangalore police. They're working metro working and also some kind of areas. They have it, but they don't have any method to transfer to the drivers. So that's why we are going to back to the drivers all this information to analyze. Hey, this is the very trusted data from municipality, from like let's say Bangalore traffic police. We have it. Then you have to be careful. That kind of things we are working on it. So why we are able to create this kind of economic mobilities? So first, we are collecting analysis mapping. It's kind of like pretty much low speed areas. Something missing right now, but maybe you can find out. And plus, we have some kind of sudden break and stress zone of these kind of situations, and then combine all together for the mapping like this. So now we can identify which area is most low speed driving and also most stress areas. So that we can find out. So maybe now we got this kind of data. Why don't you can share for the drivers? That is important. So that's why a key factor for economic the mobilities. I can several parameters here. Maybe it's a kind of like many more detailed thing, but just an example. But was you can only understand for the this kind of symbol. C is the contents, which is going to have what kind of contents to provide. And then F is the content flag. And also R is risk taking. That means some driver is pretty much aggressive. That means risk taking. Some people very conservative. It's a low risk taking. So that is kind of characteristic for the drivers. And then the G is a gyro, is a kind of like from the smartphone moving. So we can get for this kind of information. And E is an experience. How long are you living in Bangalore? Let's say like less than 20 years, 2 years, or maybe more than 5 years. That kind of information over there. And then A is accelerating from the smartphone. And then P is the position. It's each the point, junction is different. So that's why we can using this one. Finally, B is the behavior. That means it's a result. Are you understand, or are you going to decide to change for your behavior or not? So if a change behavior is the B parameter is going to 1. If not, it's going to 0. Then this is kind of like the Bayesian network. I don't explain it in detail, but it's very interesting. First, contents. Information is very important, of course. And risk-taking and experience, this is the driver's attribute, is a kind of a characteristics, how the driver looks like. All the information is comes through their drivers, like acceleration or some kind of changing. So G and A is going to be effective. Then total is B, is the kind of the behavior result. So this is kind of analytics we are calculated for this one. This is just my formula at the moment. I don't know, this is quite correct or not. We are working on it at the moment. So that's we need very nice, the science engineers, young researchers is come join with us and to help to identify what this kind of the solution mechanisms. And also solution is looks like this, and maybe content itself, we have several kind of like contents. One is caution, 12 is only for the condition, and third is guidance, change the route, and also all the information. So we have several kind of informations. But you can see this is not so significant to the kind of characteristics. However, if using like some kind of the driver's behavior, that is going to be significant change. I can show you in a minute. So these are two-dimensional results that are quite different. So in the horizontal axis is a risk taking. So you can see going to the right, it's high risk taking. It's another word is very aggressive drivers. And the vertical is information is the how many years in Bangalore. So lower is pretty much young. Higher is much more like more than 5 years living. So experience over there. Then let's say I just say example like maybe you can see the high risk and also low experience. Number 13 means guidance because they are not familiar with this area. However, they are pretty much aggressive for this. So that's why number 13 is more focused on there. But on the other hand side, in the top, P10, that means no information. In other words, high experience and high risk, that means professional. So that means I don't need any information. I can do it by myself. So these all kind of characteristics is we can calculate it using for our modeling. Maybe this is just in case, so that's like 3 dimensions informations. Just like this. It's a little bit complicated, but maybe not only just a normal regular analysis is not good enough. Point is we added like the drivers attributions or characteristics that makes some kind of difference about for the driver's behavior. That is we are working on it. So this is the kind of like the what we are doing. Then summary. So common traffic information is the doesn't always affect to the drivers. And then driver's attribute or driver's characteristic is also different and depend for the kind of like attitudes since they are the drivers. And then traffic congestion is the solution is not unique because of course improved infrastructure, but also we need some kind of some research. Then we can do it by ourselves. Then drivers' behavior change. Mode is becoming economic mobility. That is we are working on it. Of course, many people are working on it. Of course, in Japanese, all the infrastructure business ongoing in Bangalore at the moment, in the traffic signal lights improvements and also some kind of cameras on it. Takes time, more budget. But let's say we also some kind of good solution here. So let's try to do that. That is our current research activities. Again, I'm looking for nice young researchers, engineers, students. Please come to us and join with us. Our role is like this. Automotive companies and also infrastructure companies, we are standing in the middle right now. Then we also have a lot of collaboration with the all Indian and Japanese university academic and also traffic police and municipalities. We are getting to communicate at the moment. And also maybe we have some system like makers and also like startups. We are working on it. And then try to make happen to using some good solution for India. Of course, this is technology going to use for in Japan too. Then if finally, maybe good chance for joint venture, startup, real startup. We are some kind of starting to connectivities, just like a hub. Then we are generating for the many venture, joint venture solution. That is our target. And AI chip I'm looking for, definitely. To Makoto-san here. Please, we are more working on it. And also stress, that's all very important to the human characteristics. That is all information I can get for today's presentation for other members. It's very impressed. Okay. Contact information, easy. Info, mobiforum.org. That is our information. And then please remember, Mobi Forum is working hard and also with you, and especially for the Indian-Japan collaboration. We look forward to find out solution this year. Thank you very much for attention.
Thank you, Dr. Suboi, for the informative presentation. Our last but not the least, we are delighted to welcome Dr. Shreya Santra, Assistant Professor at Tohoku University's Space Robotics Laboratory, who will share insights on pioneering innovations in space robotics. Over to you, ma'am.
Thank you. So, konnichiwa, namaste, everyone, and thank you for having me here. So, I have 10 minutes to take you out of this world and bring you back here. So, I'm an assistant professor at Tohoku University, and I'm coming all the way from Sendai today. and I work on space robotics. I did my PhD as a MEC scholar in the same lab, and then started working as an assistant professor. So I'll tell you all the things that we do in space robotics and how we are pioneering innovations for the future, because now we see space has become a really interesting field where a lot of countries are getting into, and India and Japan has been a forerunner in this field. And just yesterday, US landed a lander on the surface of the moon, like a private company from the US. So it's the first private company landing on the moon. And now it's very important that we empower our population, the students, dream about going to these kind of extreme, unexplored moon, Mars, and like make it even ahead, like take our technologies ahead to these unexplored areas. In general, space robotics can be characterized into two: orbital robotics and planetary robotics. And in our lab, which was started by Professor Kazuo Yoshida, we work on both orbital and planetary robotics. Orbital robotics are robots that work on the orbits, so orbit of moon or Mars or Earth, or inside the International Space Station, or in the near the asteroids, so low gravity bodies exploring the asteroids. Planetary robotics are those that work on the surface, so on the surface of moon and Mars. In the orbital robotics, what we work on is developing different kind of motion estimation methods. Like we know that debris are becoming a major issue now in the low Earth orbit, and there's a lot of junk or unnecessary satellites or rocket fairings in the orbit of Earth, which is causing a lot of congestion. And we want to bring, trash these into the atmosphere or remove these actively. So we are developing robotic arms that can capture these debris and track these debris and then bring it back into the atmosphere where they will burn up. So we have several different kind of mechanisms that we have developed. Here you can see a cage capturing mechanism. And other than the orbital robotics, we are also working on planetary robotics. So for planetary robotics, we have two different kinds. One is the legged robot and other is the wheeled robot. So legged robots, we develop different kind of gait patterns or moving limbed robotics motions, as well as different kind of grasping techniques, so that these robots can traverse over very unstructured terrain, because on the moon or Mars, we don't exactly know what kind of terrain is there, especially if it's going inside a cave or inside a tunnel. So here you can see some examples of different grasping and locomotion techniques of these legged robots. And we have different kind of test beds where we test these robots. So here is a microgravity test bed where we try to create kind of a floating mechanism, and it's like the robot is floating using a string and then moves along that or climbs along that hill. Then here is the JAXA microgravity facility that they have, which is a mock-up of the International Space Station. And we also test our robots in these kind of environments. Coming to a mixture of legged and wheel robotics. So since we don't know where we are traversing on the moon or Mars and what kind of terrain is there, why not have a combination of both? So we came up with this transformable module, which can change from like a gripper to a wheel. And depending on what kind of terrain it is there, so by feedback from the sensors or vision sensors, it can transform from one mode to another. So we work on different kind of mechanisms like this. Coming to wheel robots, this is more specifically my area of research where I work on perception, guidance, and navigation for safe locomotion and exploration of the surface. So we developed all these kind of wheeled robots and also put on different kind of sensors on it and check our algorithms if the navigation and perception algorithms are working. So I developed these low computation, so like algorithms that will take less energy and can be implemented on these smaller robots and can be sent to the space. And basically, because we cannot send heavy things to space, there are a lot of limitations of mass, a lot of limitations of computational resources. And the more you send, the more you have to spend money wise. So we should make sure that whatever we are sending is redundant, safe, and light, and does not consume a lot of resources, a lot of power. So I develop algorithms that can be compressed in these edge devices that can be used on these smaller robots and can help the robots in segmentation or understanding its environment and safely avoiding obstacles and doing the task. One of our major goals is to have multiple robots on the surface. So instead of, like you may know, Perseverance rover or Chandrayaan, Pragyan rover, they are just single agents on the surface. But what if we have multiple agents working together, exploring that area or doing the tasks that are required in a very collaborative manner? So to do that, we develop coordination algorithms that enables these robots to share information in a very economical way. And then based on this information, they can decide which areas to explore, what tasks to do. And this also makes it even safer because it will end up not wasting your resources, not revisiting the same areas. And also the rovers will not be lost in if they keep communicating with each other. One of the very niche area that we work on is called Terra Mechanics. So Terra Mechanics is basically what the name suggests is interaction between terra, that is the earth or the soil, and mechanics, which is the wheel or the mechanism. So we study particle level interaction between wheels and sand and how they are interacting in these kind of loose sand or lunar regolith. So we have some simulants that can be that are supposed to like resemble the lunar regolith, and we test our single wheels on this kind of simulants and understand if the wheels are slipping too much or skidding too much or sinking too much, and accordingly we design the wheels for our rovers. So this is a single wheel test, and then we study the single wheel test and then make the full rover and also the suspension systems that can support this kind of wheels. So in our lab, we have the fastest single wheel test bed in the world, which can run at 20 kilometers per hour. And here actually we are testing the lunar polar exploration rover, which is being developed by JAXA, and it's a joint mission between India and Japan. So we are testing in this facility and then also developing high-speed rovers that can help explore the area in a faster manner. However, going to moon or access to these kind of test beds or access to analog sites is not really very easy. So we also develop simulators that can help test our algorithms before we deploy on the hardware. So you don't risk the hardware until you're 100% sure that your simulations and your algorithms are good enough. So we have developed this, it's an open source simulator right now. It's a photorealistic simulator where we try to make it exactly how moon would look and also the physics that are involved with it. and we test our perception, navigation, algorithms on it. And we have seen that the results are very promising as we have validated it also with like real world data. And bringing all of this together, currently we are working with the Moonshot project, which is supported by the Japan Science and Technology Agency under the goal called Goal 3. And the topic is self-evolving AI robotic system for lunar exploration and human outpost construction. So we are building modular robots that can reconfigure and that are heterogeneous and can reconfigure into different heterogeneous forms depending on the tasks that they can do. Also, they can learn from each other and learn from their own actions, as well as they can repair and fabricate on the site, so on the moon. So you don't have to send replacements all the time to Moon or Mars. So currently, this is a test that we did last year at the JAXA lunar facility, where we tested our modular robots, which were like, as you can see, like different heterogeneous modules can be changed and reconfigured into different forms depending on the task that they have to do. Again, these are the same modules, and they are doing different kind of
Sorry,
tasks,
ma'am,
like assisting.
I would like
2
you to
minutes.
conclude this presentation, please.
Yeah, so this was the test, and again, from tomorrow onwards, the whole month, I'll be doing tests with our robots for our at the JAXA facility. So why is it important? Now coming back to Earth, why is it important? Because these robots can help also on Earth. And with this, I would like to end my talk. And if anyone's interested, you can connect with me. And yeah, thank you so much.
Thank you, Dr. Santra, for your fascinating presentation. This concludes our scientific talk session. Moving on with our next session. Good evening, ladies and gentlemen, honorable ministers, excellencies, distinguished guests, esteemed scientists, and participants. A very warm welcome to you all. Today, we are celebrating India's National Science Day 2025. We also avail this opportunity for a curtain raiser event for the 2025-26 as India-Japan Year of Science, Technology, and Innovation Exchange. We are privileged to have you all with us today, and once again, our sincere gratitude for joining us. It is my privilege to invite His Excellency, Ambassador Mr. Sibi George, Ambassador of India to Japan, to deliver his address to begin the celebration.
Good afternoon, everybody. Honorable Minister of State, Independent Charge, Ministry of Science and Technology, Ministry of Earth Sciences, Minister of State in the Prime Minister's Office, Department of Atomic Energy and Department of Space of India, His Excellency Dr. Jitendra Singh Ji, Honorable Minister in charge of Economic Security, Minister of State for Cool Japan Strategy, Intellectual Property Strategy, Science and Technology Policy, Space Policy of Japan, His Excellency Mr. Kyuichi Minoru, Honorable Minister of Education, Culture, Sports, Science and Technology, MEXT, Japan, Her Excellency Ms. Toshiko Abe, Secretary, Department of Science and Technology, Professor Abhay Karandikar, Senior Deputy Minister of MEXT, His Excellency Masuko Hiroshi, Director General of MEXT, Mr. Inoi Yuichi, President of JAXA, Mr. Hiroshi Yamakawa, President of NIMS, Professor Kazuhiro Hono, President of GISTEC, Mazuo Aizawa, Vice Presidents and senior officials from the government departments, universities, and science and technology institutions in Japan, and also those who are joining online from India, our dear young budding scientists from the schools who exhibited their passion for technology and science through their projects today morning, ladies and gentlemen. It gives me immense pleasure in welcoming our excellencies on this occasion of the India's National Science Day 2025 that we are celebrating today at the Embassy of India. The February 28, the day of discovery of Raman effect, is celebrated as National Science Day in India. I am thankful to Honorable Minister Dr. Jitendra Singh and Honorable Minister of Japan, Honorable both Ministers of Japan who have joined us today in celebrating this great occasion. Today we are celebrating also as the curtain raiser of our India-Japan Science and Technology and Innovation 2025. Dear friends, this year's celebration is special as we are commemorating the 40th anniversary of the formalization of science and technology cooperation between India and Japan. The theme, Empowering Indian Youth for Global Leadership in Science and Innovation for Vikasit Bharat, highlights the intentions of India's youth contributing and providing global S&T leadership, so as to fill the gap of participation of youth in Japan's S&T ecosystem too. Your Excellencies and dear participants, as you know, to commemorate the 40th anniversary of this science and technology MOU that we have signed, this year we are celebrating India-Japan Year of Science, Technology and Innovation Exchange. I convey my sincere gratitude for gracing this occasion. Your continued support will elevate India-Japan Science and Technology partnership to new heights. I am sure that this partnership will harness each other's strength in order to meet our respective national goals. Science and technology and innovation are central to transforming countries and reshaping the global order. India's partnership with Japan holds a special space in this context. Cooperation in science and technology would contribute in its own way to the clarion call Honorable Prime Minister of India, Mr. Narendra Modi ji, has given for Vikasit Bharat by 2047. The cooperation would also play a crucial role for Japan in regaining its technological strength in new and emerging world with a fast technological advancement. It may be by involvement of more and more young innovative minds participating in Japanese science and technology activities and vice versa. Dear friends, I am very happy to remind that this year we are celebrating the 10th anniversary of the special strategic and global partnership that India and Japan entered into in 2014. During the last 10 years, our relationship has evolved into what we call a really special strategic partnership. And in this, science and technology plays a very important role. We used to say that sky is the limit for our relationship. But let me tell you, sky is no more the limit. Even space is not the limit. We are cooperating very well in sky and in space. And in coming months and years, we will continue to work together between India and Japan, involving all our science and technology institutions, all our faculty in science and technology, all our students and research scholars in science and technology, to build a momentum so that we could have more engagement, closer engagement in science and technology and also in innovation. India today is the third largest startup ecosystem in the world. India and Japan can work together to build further these innovation initiatives to take our two countries forward. One area where we are working very closely is the semiconductor area. We have seen that Japan in the last few years is making tremendous progress in the field of semiconductors, and I'm very happy that India is also focusing on semiconductors. There are so many modern technology areas, critical technology areas, where our two countries can work together and progress together. The decision to celebrate India-Japan Year of Science and Technology and Innovation is a great step in building this relationship. We have a series of events planned, as I said, involving all the major science and technology institutes in India and Japan. Once again, I thank each one of you for joining us. Honorable Minister Dr. Jitendra Singh, Honorable Minister of Economic Security and Science and Technology of Japan, Mr. Kiichi Minoru, Honorable Minister of MEXT, Dr. Ms. Toshike Abe. We have also the President of JAXA with us, President of NIMS and President GISTEC, and also other dignitaries. I once again welcome each one of you. Thank you and good evening.
Thank you, His Excellency, for your kind address. We are honored to welcome His Excellency Dr. Jitendra Singh, Honorable Minister of State for Science and Technology, Minister of Earth Sciences, Department of Space, India. We are grateful to you, sir, for kindly joining us online from India to grace the occasion. We invite you, sir, for your kind address.
Sir, no audio, sir.
Good afternoon, everybody.
Yes, sir.
Today, on the occasion of the celebration of the National Science Day 2025 by the Embassy of India in Tokyo, it is my pleasure to grace the occasion and also to address the gathering on the theme that we have chosen for this year's National Science Day, that is empowering Indian youth for global leadership in science and innovation for Viksit Bharat. National Science Day has been celebrated in India on the 28th of February. I thank His Excellency Mr. Khushi Minoru, Honorable Minister of State for Economic Security, Science and Technology Policy, Space Policy of Japan, Her Excellency Ms. Abe Toshiko, Professor Abhay Karandikar, Ambassador C.B. George, the Ambassador of India to Japan, dignitaries, ladies and gentlemen. I'm glad to say that the Indo-Japan science and technology cooperation is one of the strong pillars of our international science and technology engagements. Following the intergovernmental agreement, which was signed way back in 1985 between the Ministry of External Affairs, New Delhi, and the Ministry of Education, Culture, Sports, Science and Technology of Japan, our External Affairs Ministry, in a recent bilateral meeting in January 2025 in Washington, D.C., declared 2025-26 as the India-Japan Year of Science, Technology, and Innovation. Both the ministers also welcomed efforts to enhance people-to-people exchanges, especially in the areas of technology, skill, and education. I'm glad to inaugurate the Curtain Raiser event for India-Japan Year of Science, Technology, and Innovation exchange commemorating our 40 years of S&T partnership, as was being mentioned by the ambassador as well. India plays a major role in the R&D purposes for all sectors of science and technology, with multi-stakeholders of academia, R&D institutions, entrepreneurs, while keeping scope for equal opportunities for participation of women and young scientists. And it is heartening to note that Prime Minister Honorable Narendra Modi is very forthcoming, supportive, patronizing in all our scientific endeavors, domestically as well as with the other nations, including Japan, with which India has shares a special relationship. India, you would agree with me, is actively contributing to the participation and involvement with international and regional forums. The 11th meeting, ladies and gentlemen, of the India-Japan Joint S&T Committee is expected to be conducted in the month of June this year, which channelizes new initiatives as well as reviews the ongoing science and technology cooperation between the two nations. Now, as far as the Japan Society for the Promotion of Science is concerned, since 1993, till date, more than 300 joint projects were supported with Japan, and more than 1,000 exchange visits of scientists and scholars have taken place, including numerous seminars and workshops. And in the last 10 years, under the Modi regime, this has received a special impetus and focus. In fact, I may add over here, ladies and gentlemen, that together with Japan Science and Technology, or the Japan Science and Technology JST, we are working for the joint program on supporting projects in newer areas like artificial intelligence, like machine learning, and also certain more emerging fields of S&T. It is also heartening to know that the Indian students are actively participating in different scientific meetings organized by Japan, such as, for example, the HOPE meeting with Nobel laureates, the Asian Science Camp and Skura exchange activities. And I may add over here that a local of about 7,000 science students from India visited Japan under the Sakura Science Program since 2015, who were selected by the Department of Science and Technology, Government of India, the Ministry of Education, Government of India, and also with the invitation by the Japan Science and Technology and the universities in Japan with support of JST. We are also going to increase the number of exchange visits of students and researchers for further strengthening of our S&T cooperation. This would include long-term stays, joint supervisions, special focus on talented women science students, and also internship positions in Japan. The Department of Science and Technology, Government of India, has also invited Japanese science students for exposure visits in India. In the last 1 year, 10 such students with 2 supervisors visited India. University and institutes regularly invite students under the Skura Science Program to their institutes in India and the partner institutes in India. India, as you would agree with me, has been progressing and processing consecutively its science and technology activities on a globally competitive arena with inclusiveness and holistic approach. India today, I'm glad to share, has achieved 3rd position in the term of research publications, 3rd also in the terms of the number of PhDs, 3rd also in the number of startups in the world, and 3rd also in the terms of unicorns in the world, while 9th in the quality of research publications and 39th in the Global Innovation Index, which ranked 81 before Prime Minister Modi came in 2014, and today has shown a quantum jump to 39. We have incubation centers aimed to facilitate the academia and industry partnership for nurturing science, for nurturing technology, and nurturing innovation in the country. The success of Chandrayaan-3, which was the first to land on the southern pole of Moon, is an achievement which has been globally hailed by the entire world. Our space program is one of the strongest. We had 104 satellites launched in a single flight by ISRO, which is in itself a world record. That took place in 2017. And I'm glad that in the last 5 or 6 years after Prime Minister Modi allowed us to open the space sector to the private sector, the private players, there has been a quantum jump both in the terms of investment as well as the quality of space missions. There is also a lot of industrial development seen and many service sectors have been engaged with this. India, through the Department of Science and Technology, has been implementing national missions in cyber physical systems, in electric mobility, in quantum science, in clean energy, in solar sector, in hydrogen, also including high performance computers and national climate actions. We are deeply looking at deep tech sector. We also look forward in the creation of joint center by Japan and India for accelerated innovation on science and technology to address the critical S&T challenges of both the countries, including the global challenges such as sustainable development and the sustainable development goals. We could identify gap areas in science, technology, innovation, and enable wider engagement for future partnership in a way that could serve the interest of both our countries while at the same time addressing critical challenges for a sustainable, safe, and secure future. I take this opportunity, ladies and gentlemen, to once again congratulate the Embassy of India in Japan and the Ambassador George for organizing this event. Thank you. Thank you and namaste.
Thank you, His Excellency, for inspiring us. May I now request His Excellency Ambassador Mr. Sibi George, His Excellency Minister Kyuchi Minoru, and Her Excellency Minister Toshiko Abe, and other dignitaries as requested to please join us on the stage for a group picture with Honorable Minister Jitendra Singh Ji. Thank you, His Excellencies. As we are celebrating National Science Day, we planned a little surprise, a quiz to enjoy and take a dip in the ocean of scientific knowledge. We'll take one question between each speech. So it's quiz time.
Thank you. So it's interesting to again interact and indulge in scientific questions. So this question is for young minds. All you know, today we are celebrating National Science Day as tribute to Bharat Ratna Sir C.V. Raman, who discovered the Raman effect. So what do you understand by Raman effect? The question is it scattering? It is a scattering of what? It's a scattering of molecules, option A. Option B, the scattering of atoms. Then option C, scattering of photons or scattering of microwaves. So what is the answer? So generally, what you see, you look for, that's a word called light, but it gives a hint to you. So y'all young students, so first, the girl who raised the hand here. Correct.
Option C, scattering of photons.
So first winner. Your good name?
Janvi.
Janvi. Congratulations for winning this.
Thank you.
Thank you.
Next, we have the privilege of hearing from His Excellency Minoru Kiuchi, Honorable Minister of State for Economic Security, Science and Technology Policy, and Space Policy of Japan. May I now take the honor of inviting His Excellency Minoru Kiuchi to share his remarks. ただいまより経済安全保障、科学技術政策担当、宇宙政策担当大臣のミノル木内様よりご挨拶をいただきます。どうぞよろしくお願いいたします。
はい。Your Excellency Jitendra Singh, Honorable Minister of State for Science and Technology, Your Excellency Ambassador C.B. George, ladies and gentlemen, I'm Minoru Kiuchi, Minister of State for Science, Technology and Technology Policy and Space Policy. Thank you for inviting me to this event in celebration of India's National Science Day 2025 and the start of the Japan-India Science, Technology and Innovation Exchange Year. I'm very grateful to Ambassador C.B. George and everyone at the Indian Embassy for their warm invitation. I'm delighted to note that this year marks the 40th anniversary of the signing of the Japan-India Science and Technology Cooperation Agreement. To commemorate this milestone, we have designated the period from this April to next March as the Japan-India Science, Technology and Innovation Exchange Year, during which we will further deepen our cooperation in the fields of science and technology. For example, we have both recently achieved significant results in space exploration. In August 2023, the Chandrayaan-3 probe made India the fourth country in the world to successfully land on the moon, which was followed by Japan's SLIM probe, making us the fifth in January 2024. Now, a joint Japan-India lunar exploration project called LUPEX is underway, and it is my hope that Japan and India will continue to collaborate and innovate together. In order to further strengthen the ties between Japan and India in the future, it is essential that we deepen exchanges among our experts in the fields of science and technology. At the Japan-India Summit meeting last October, both Prime Ministers expressed their intent to further promote these people-to-people exchanges between our two countries. In Japan, such people-to-people exchanges with India in science and technology have been promoted by the Ministry of Education under Minister Toshiko Abe, as well as by universities and research institutions. And recently, I have been delighted to see local governments also actively working on collaboration with India, including interpersonal exchanges. For example, in December last year, my home prefecture of Shizuoka concluded a friendship agreement with Gujarat, aiming to promote cooperation and exchange in a wide range of fields, including the economy and education. I hope that Shizuoka will be able to deepen its cooperation and friendship with Gujarat state, which has achieved what has been called the Gujarat miracle of economic development under the strong leadership of Prime Minister Modi. I have high hopes that through a variety of initiatives at the national and local levels, we will be able to promote people-to-people exchange and joint research in information technology and other areas, empowering the creation of an innovation ecosystem linking India and our country. These initiatives will also undoubtedly contribute to the theme of today's event, empowering Indian youth for global leadership in science and innovation for Vikshit Bharat. In conclusion, I hope that today's event will be fruitful and contribute to both the further success of all of you here today and to the positive relationship between Japan and India. Thank you for your kind attention.
Excellency. Now again a quiz time.
Thank you. So when we talk about science and technology, we are on the moon together. We are on the moon together. So the question one question we need to have relating to moon mission, the Chandrayaan-3. And this question will be only for Japanese because Indians would, understand it differently. So any moon mission will have three components. One is rover, one is orbiter, and one is lander. So which part of the mission Chandrayaan did not have in the moon mission? Option A, Pragyan rover, Aditya orbiter, and Vikram lander. Or all of above were there as a part of the Chandrayaan-3 mission. And the question only for Japanese. It's a very simple question. So, so one is rover, one is orbiter, and other is lander. So there are Hindi names to it: Pragyan, Aditya, and Vikram. So which one was not part of this Chandrayaan-3? So can we transfer these questions to the young minds from schools? Yes. Yes. Aditya L1 was not a orbiter for the moon. It was actually different mission to measure the sun magnetism and the activities on sun. So at L1 point, the Aditya. Thank you. Your good name? Yes. Okay.
We are now honored to invite Her Excellency, Minister Toshiko Abe, Honorable Minister of Education, Culture, Sports, Science and Technology of Japan to deliver her address. 文部科学大臣Toshiko Abe 様よりご挨拶をいただきたいと思います。よろしくお願いいたします。
Hello, everyone. Ambassadors C.B. George, Minister of Science and Technology, Jitendra Singh, distinguished guests. Namaste. I am Toshiko Abe, Minister of Education, Culture, Sports, Science and Technology of Japan. It is my great pleasure to celebrate India's National Science Day with you. This special day celebrates remarkable discovery of the Sir Chandra Shekhar Raman, the first Asian to receive Nobel Prize in Science. The second Asian literate was Dr. Yukawa, was from Japan. This highlights how India and Japan have been leading science and technology in Asia. These two countries will launch the Japan-India Science Technology and the Innovation Exchange Year in April. And in line with this, We next will significantly expand support for Indian graduate students conducting research in Japan. I hope this anniversary year will further deepen the partnership between Japan and India. Dhanyawad. Thank you very much.
We thank you, Madam Minister, for your address and sharing your insight. Arigatou gozaimashita. Now we have the quiz time again.
Thank you, ma'am, for the address and the deepening relationship, and then we are heightening it to the next level. So next question is now come from the scientific work in Japan, which is used all over the world, and in India we are extensively using the QR code. So Masahiro Hara, who has invented QR code, and then all the financial transaction in India happens using the QR code. So this question now would be for the Indians to answer what is the full form of this word QR code. So there are so many hands. I will not take those hands which belongs to IT. So the first option is the qubit reading code, or the quite reliable code, or the option C, quick response code, and fourth option is question row code. So which one? So I will not take hands which are from IT. So yeah, young students. So who raised the first there? Hand. So yeah, yes, yes.
3 quick response code.
Correct. So it responds very quickly to make your payment, get you access to the airport, get you access to the railway station in Japan. So I think very interesting and very, very widely used invention.
After all the inspiring speeches, we are ushering into the second phase of the program, the awards and honors segment. But before that, it's quiz time again.
I think, yes, that would be my last quizzing you all. So no more for question after this. So we would be in India, very interesting concept. Anybody can get a license to transmit radio waves in certain frequency, and they can become communicator. They can by hobby. So you have a license for that, you apply to it, and you can talk to next building, you can talk to other places, far off places, and you can have your own broadcast. So that license is given for hobby purpose, but what that licensee is called? And this question for everybody. So options here: radio jockey, broadcaster, radio anchor, ham. So, oh, the answer from Japan here, please. Yeah, great, correct.
Thank you, sir. May I now request His Excellency Ambassador Mr. Sibi George, His Excellency Minister Kyuichi Minoru, and Her Excellency Minister Toshiko Abe to kindly join us on the stage once again for awards and honors ceremony and oblige awardees with group photographs. We now invite the winners of the weekly science and technology quiz to come up on the stage for a group photo. Thank you. May I now request the dignitaries and excellencies to please remain on the stage, please. And I now request the winners to go back and take their seat. So we are going to have one more photograph session. We had an exciting scientific talks today, so we would like to invite esteemed speakers of today's scientific talks to kindly join us on the stage for a group photograph. Thank you so much, sir. I would like to request excellencies and dignitaries to please be on the stage. We have another group photograph. Now I would like to request today's quiz winners to come up on the stage and for a group picture. Thank you, His Excellencies. May I now request His Excellency Ambassador Mr. Sibi George to present mementos to His Excellency Minister Q.T. Minoru. Thank you, His Excellency. May I now request His Excellency to present mementos to Her Excellency Minister Toshiko Abe. Thank you, His Excellencies. With this, we formally conclude the inaugural session of today's event with tribute to Bharat Ratna Sir C.V. Raman on the occasion of National Science Day. With sincere gratitude to dignitaries online, especially Honorable Minister Dr. Jitendra Singh Ji, we take leave and usher into conclusion of the program today. We now invite Excellencies and other esteemed guests to join us for the reception to celebrate the spirit of India-Japan science and technology collaboration and begin the year-long celebration of India-Japan Year of Science, Technology and Innovation. Excellencies, our staff will escort you. Once again, I invite you all to join us to have the great time at discussion during the reception. Thank you for your gracious presence. Have a wonderful evening. 以上をもちまして本日のイベントを終了とさせていただきます。ありがとうございました。 you.